Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from University of Ontario Institute of Technology, also known as Ontario Tech University. I also took my Bachelor's of Science at this institution as well in the Pharmaceutical Chemistry program. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now I'm just going to get started on our set of questions in today's session. Okay, so question 1 asks, what is the electron configuration of carbon? So first I'm going to write down the definition of electron configuration, since it might be a new term for some of the viewers. Electron configuration is the distribution of electrons in atomic or molecular orbitals. So there are different steps that we can take in order to find the electron configuration of a certain atom. So I'm going to write down the steps right now. So step 1 is to divide the periodic table into atomic orbital sections. So I just looked up on Google an example of this. So here are all the electron configurations in the periodic table. In the light blue section here, and also helium, this is from the s orbital. The green section over here is the p orbital. The middle part of the periodic table is D. And the last two rows, the lanthanides and actinides, are the f orbital elements. So this brings us to step 2, where you just move from left to right across the rows. And you start at hydrogen. And then when you write it down, you write the row number, then the block letter. So this will make more sense when I do the example for the question. Step 3 just says that when you get to the D part of the periodic table, so for the D orbitals, the D block, the row number will be -1. And similarly for the F block orbitals, it's the row number -2. So let me write down the example for carbon. Excuse me. Okay, so for example, for carbon, go back to the periodic table. So first let's find carbon on the periodic table. It's right here where the mouse is. So starting from hydrogen and going from left to right, I first write down the row number, just say carbon. So the row number starting at hydrogen is 1, and then its block letter is S, and then going across, helium is also in the 1s orbital, and to show that there are 2 electrons, helium, the 2 in helium and the 1 in hydrogen, I put 1s2. So you can think about each extra electron as one of the numbers in the superscript. Okay, so 1s2, and then going back to the row number 2, it's going to be 2s2. So this shows the lithium and the beryllium. And then going across to 2p, and then going to count up to where the carbon is. So 1, 2 is where carbon is. So the electron configuration for carbon is 1s2, 2s2, 2p2. I'll also write a note that for some transition metals, a filled d orbital is more stable than when you have a partially filled. So sometimes when you have an ion, and let's say it ends in 4s1, 3d9, or 4s2, 3d8. You can also write it as 3d10. So sometimes that is the preferred electron configuration. That's just an example. But let's see what the junior tutor said. Carbon is in group 14. Group 14 elements have 4 valence electrons. Carbon is in period 2, meaning the highest energy level is 2. Each energy level there is 1 s orbital and 3 p orbitals, except n equals 1, which only has 1 s. S orbitals have a maximum of 2 electrons, and the 3 p orbitals can have a maximum of 6, so the electron configuration of carbon is equal to 1s2, 2s2, 2p2. Yep, so this solution is correct. Now let's move on to question number 2. Using SPDF notation, give the electron configuration for vanadium, which is an element found in some brown and red algae and some toadstools. So I'm just going to write it on the right side here. Just so that we can see the rules again. Okay, so question 2 asks for vanadium. Vanadium. Okay, so again, let's look at the periodic table. And you can see vanadium is right here where my mouse is. And then we're going to do the same process we did for the carbon, starting from hydrogen and moving from left to right. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then counting up to vanadium, 1, 2, 3, so 3d3. Okay, so we can also write the electron configuration in the shorthand way. So to do this, we are going to find the noble gas that comes right before vanadium if you go in order. So before vanadium is argon. So to write the shorthand way, I'm going to do argon in square brackets. And then you just continue on with the same rule. So argon, 4s2, 3d3. So this is a faster way of writing the electron configuration without having to write all of the 1s2, 2s2 steps. Okay, so the junior tutor said, electron configuration is the distribution of electrons of an atom across different orbitals. The distribution of electrons is governed by the following. Aufbau principle states that orbitals are filled up with electrons in increasing energy. Example, the lowest available energy levels are filled up first. In connection with the above, the Madelung rule, or Kleczkowski's rule, states that orbitals with a lower n+1 value are filled first. Hund's rule states that the most stable arrangement is the one with more parallel spins, meaning orbitals are filled first with unpaired electrons before they are paired. Lastly, Pauli exclusion's principle rule states that an orbital can have a max of 2 electrons with opposite spins. Vanadium is a transition metal with atomic number 23. It has 23 electrons in its ground state. Following the rules above, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2, and its noble gas core electron configuration is argon 3d3, 4s2. So some people write the 4s2 before the 3d3, but I've seen it being written as both ways. But this solution is correct. Okay, so on to question 3 is another electron configuration question. What is the electron configuration for an aluminum ion, aluminum 3+? So whenever I have electron configurations that require an ion, I like to first write down the electron configuration of the atom, of the neutral atom. So in the case of aluminum, let's start from hydrogen and then go across to get its electron configuration. So for aluminum, it is found here, and it just goes 1s2, 2s2, going to 2p6, and then 3s2, and then finally 3p1. And we can also write down the shorthand configuration. The nearest noble gas that comes before aluminum is neon. So I can write neon in square brackets. And then continuing on, 3s2, 3p1. Okay, so now the question asks for the electron configuration of aluminum 3+. So when you have 3+, since electrons are negatively charged, this means that 3 electrons were removed. So now, let's look at the electron configuration of just regular aluminum, and then we're going to take away 3 electrons. So basically the last 2 parts there. So now its new electron configuration is 1s2, 2s2, 2p6. Or it just has the same electron configuration as neon. Okay, so let's see what the junior tutor said. To answer this, we need to determine first the electron configuration of the elemental aluminum. By inspecting the periodic table, aluminum belongs to period 3, group 13, and has an atomic number equal to 13. The atomic number tells us that the neutral form of aluminum must account for a total of 13 electrons. Therefore, the configuration of aluminum in elemental form would be 1s2, 2s2, 2p6, 3s2, 3p1. Now we have the aluminum ion, aluminum 3+. 3+ here means that aluminum loses 3 electrons from its outermost energy shell. In this case, the 3 electrons lost would come from the third energy shell, 1 from the 3p orbital, so shown here, and then 2 from the 3s orbital, which was this one. This means the electron configuration would be 1s2, 2s2, 2p6. Yep, so I can verify that this solution is correct. On to question number 4. How many quarts are there in a gallon? Well, we can just simply say that there are 4 quarts in 1 gallon. And the junior tutor said, use the conversion factor 4 quarts over 1 gallon to solve for the number of quarts in 1 gallon. Yep, makes sense. So number of quarts is equal to 1 gallon times 4 quarts over 1, which is equal to 4 quarts. Yep, so solution is correct. Nice way to show how to use conversion factor. So let's say we wanted to know how many quarts there are in like 15 or like 25 gallons. The way that the junior tutor showed is how you would do that by using conversion factors. So the solution is correct. Question 5 just asks, how do you find the pH at the equivalence point? So first I'll write down the definition of equivalence point. So this happens when the amount of titrant that is added is enough to completely neutralize the analyte solution. Okay, so I'm just going to give out an example. Of if you have a strong acid, let's call it HA, that completely dissociates into its ions H plus and A minus. If the concentration of HA was, let's say, 0.5, this is the initial concentration of our reactant. And initially, we have a concentration of 0 for both of our products. The C means change. So during the reaction, there's going to be minus X change for the reactants as it is being turned to the products. So the change for the reactant is minus X, and for the products, it's plus X. Then lastly, at equilibrium, it's going to be 0.5 minus X, and X will be equal to the concentration of both of our products. So let's say there was a Ka value given. It's usually around like 4 point something times 10 to the negative 6, let's say. This Ka value is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA. So if we sub in our values from the ICE table, we can say 4.9 times 10 to the negative 6 is equal to x times x, which is x squared, divided by 0.5 minus x. So using a quadratic formula to solve for x, you end up getting a value equal to 1.56 times 10 to the negative 3, which is also equal to the concentration of H plus. So we want to know the concentration of H plus because in order to calculate for pH, it's going to be the negative log of the concentration of H plus. So for this example in particular, pH will be equal to negative log of 1.56 times 10 to the negative 3, which is equal to 2.81. Okay, so that's one way of doing it when you have a strong acid. And for the junior tutor's answer, they said to consider the titration of a weak acid by a base OH minus. So this requires a little more steps than just having a strong acid example. So they say to consider this titration. So this is the reaction where the weak acid plus OH minus makes A minus plus H2O. The ICE table for Z moles HA titrated with X moles of OH minus is given below. Note that Z is equal to X. So here they have like a similar ICE table. As seen in the table above, all of the HA and OH- have reacted with each other to produce A- and H2O. This means that the pH of the solution is only due to the hydrolysis of the conjugate base A-. Hydrolysis of the conjugate base is shown in equation 2. So here they show A- plus H2O makes OH- plus HA. So it basically looks like the reverse reaction of the first one. The base dissociation constant expression for equation 2 is given below. So since this is our A- dissociating to OH, instead of using a Ka expression, they use a Kb expression, which is equal to the concentration of OH- times the concentration of HA divided by the concentration of A-. So here is the ice table for the hydrolysis shown in equation 2. So we substitute the equilibrium expressions into equation 3 and solve for x. Note that x is the concentration of OH- and HA. Then we can get the pH in two ways. First, calculating the concentration of H+ using the auto-ionization of water. So this is another equation where Kw is equal to the concentration of H+ times the concentration of OH-. And Kw has a value of 1 times 10 to the negative 14. Recall that the pH of solution is related to the H+ concentration through equation 5. So pH is equal to negative log of H+. Another way to get the pH is by calculating the pOH and by using the relationship between pH and pOH. We calculate the pOH in the same way that we calculate pH. Then the equation that relates pH to pOH is obtained by getting the negative logarithm of equation 4. And you can double check your answer by seeing if pH plus the pOH is equal to 14. But basically this solution is correct. Okay, so on to question 6. Is 1 gram equal to 1 milliliter? So 1 gram is a unit of mass, and 1 milliliter is a unit of volume. So we can say that 1 gram is not equal to 1 mil, since 1 gram shows mass and 1 mil is volume. So it all basically depends on the density of your material. So let's say we had 6 grams of rocks is equal to like if you were to fill up a 10 milliliter cup, so 6 grams of rocks takes up like 10 mils, let's say. But let's say we have 6 grams of like feathers. You would need way more feathers to get 6 grams. Let's say you need like a whole 2-liter volume of feathers. So that's the reason why 1 gram isn't equal to 1 mil. The only time where it does is for pure water. So water has a density of 1 gram per milliliter. So we can confidently say that 1 gram of water is equal to 5 mils of water. And that is the only case where 1 gram will equal 1 mil. So if it has a density of 1. But let's see what the junior tutor said. No, gram is a unit of mass, while milliliter is a unit for the volume of liquid. Mass and volume are related in terms of density, where density is directly proportional to mass and inversely proportional to volume. Density equals mass over volume. The only time 1 gram is equal to 1 mils is when the density is 1, which is only the case for pure water. Yep, so the solution is correct. Okay, so I think we are on question 7. How do you convert grams to moles and moles to gram? So the main equation for this type of question is number of moles is equal to mass over molar mass. So molar mass of a compound, you can find the values on the periodic table. And if we know the molar mass of a compound, then we can calculate for number of moles, or we can calculate for mass depending on what we're given. So the short form is saying N is equal to lowercase m, and molar mass, you write uppercase M. And if we wanted to solve for moles to grams, we basically just need to rearrange this equation. So bringing the molar mass over to the left side, finding mass is equal to the number of moles times the molar mass. So it just all depends on what you're given in the question. But let's see what the junior tutor said. Dimension analysis is key. Multiply the given quantity with a conversion factor that will eliminate the given unit and bring up the desired unit. For example, to convert 120 mole, I think they mean grams of water to moles of water, use the conversion factor 1 mole over 18.02 gram H2O. So that's the same thing as saying its molar mass is 18.02 grams per mole. 18.02 grams per mole is the molar mass of water. So 120 grams divided by 18.02 grams per mole is equal to 6.65 moles of H2O. They have another example of converting 120 moles of oxygen molecule O2 to grams. This is where you would just multiply by the molar mass. So 120 moles of oxygen times 32 grams per mole is equal to 3,840 grams of oxygen. So this solution is correct. And we can move on to question number 8. So question 8 asks, how do you calculate the oxidation number of an element in a compound? So first let's write down the definition of an oxidation number. So oxidation number is the charge that that atom would have if the compound was composed of ions. So ion just means an atom with a charge. So I'm going to look at the Janine The Tutor's answer because they have all the different rules of how you would calculate the oxidation number. And then I'll just go over some examples. So here are some of the rules. The oxidation number of a free element is always 0. So if we had like a pure solid or a pure gas, it would have a 0 as its oxidation number. Oxidation number of a monatomic ion equals the charge of the ion. Oxidation number of hydrogen is +1, but it is -1 when combined with less electronegative elements. So if hydrogen was a hydride. Oxidation number of oxygen in compounds is usually -2, but it is -1 in peroxides. Oxidation number of a group 1 element in a compound is +1. Oxidation number of a group 2 element in a compound is +2. And same with group 3 elements as well. It's +3, but that's not there. The oxidation number of a group 17 element in a binary compound is -1. And the sum of the oxidation numbers of all the atoms in a neutral compound is 0 because your compound is neutral. And the sum of the oxidation numbers in a polyatomic ion is equal to the charge of the ion. Okay, so now that we know all of the rules, let's do some examples. Let's say we had aluminum sulfide, and we want to find the oxidation number of the sulfur atom. So this compound is neutral. So I'm going to write a 0. And then to try and solve for the oxidation numbers, since rule number 8 says the sum of all the oxidation numbers of all the atoms is 0 of a neutral compound, I'm going to do 0 is equal to 2 aluminum, since there are 2 atoms of aluminum, plus 3 sulfur, and then plus 12 oxygen. So in the brackets, I am now going to put in the oxidation number of each of the atoms. So aluminum is a group 3 element, and it has an oxidation number of +3. And rule number 4 says the oxidation number of oxygen is usually -2. So since this is not a peroxide, oxygen has an oxidation number of -2. So I'm just going to plug those values in. So there's 2 atoms of aluminum plus 3. Okay, that's clear. And we're looking for S. And it's going to be 12 times -2. So it's going to be 6 plus 3S minus 24. And now we just solve for S. So let's bring that over to this side. S is equal to +6. Okay, so the sulfur has an oxidation number of +6. I'm gonna do another example on the right side. So let's pretend that we had a charged compound, like a polyatomic ion. So for example, let's say we had H2PO4 minus. And we want to find the oxidation number of the phosphorus. So since this ion has an overall -1 charge on the left side of the equation, I'm going to do -1 because rule number 9 says that the sum of the oxidation numbers in a polyatomic ion is equal to the charge of the ion. So -1 is equal to 2 times the oxidation number of hydrogen, since there are 2 atoms of hydrogen, plus phosphorus, plus 4 times the oxidation number of oxygen. Okay, so let's recall that hydrogen, so this isn't a hydride, so each hydrogen atom has an oxidation number of +1, and each oxygen atom has an oxidation number of -2. So now let's just plug in those values. And then solve for the unknown. So we end up with an oxidation number of +5 for phosphorus. Okay, so those are just some examples of how you would calculate the oxidation number. And I'll just say for the junior tutor, this solution is correct. They gave all of the rules on how we would solve for it. Okay, so now let's move on to question number 9. Yeah, so question 9. How do you calculate number of moles from milliliters? Okay, so easiest way to do that is by using this concentration formula, where concentration is equal to number of moles over volume. So if we know the concentration and we know the volume, we would just need to multiply those two values together to get the number of moles. So another way to do that, so this is for solutions. If we had like an ideal gas and it wasn't like a liquid, we can also use the ideal gas formula, which is PV equals nRT. So it just depends on what you're given in the question. So P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is temperature. And we can rearrange this to solve for the number of moles. Again, it's just what depends on what you're given, and it depends if you have like a solution or if you have like an ideal gas. But let's look at the junior tutor's answer. Yep, so to answer just depends on what information is given. If you're given a solution, we can use its molarity. So I said concentration, but molarity is like the same thing. To relate the number of moles to of the solute to the volume of the solution. And you can do number of moles is equal to concentration times volume. And they also have the ideal gas equation as well. Number of moles is equal to PV over RT. So the junior tutor also added if we are given the density of a substance, recall that density is how much volume of a mass of a substance occupies. So density is equal to mass over volume. We can use the molar mass of the substance to relate the mass of the substance to its equivalent in moles. Yeah, so that's another way of doing it as well. You can get number of moles is equal to density times volume divided by the molar mass. Yep, so this solution is correct. Okay, so on to question 10. What is the chemical formula of graphite? So graphite is an allotrope of carbon. So basically, it is made up of repeating units of carbon. So graphite and diamond have this in common, where it is just repeating units of carbon. So for example, you can have like a graphite pencil. So there's no like specific chemical formula. So if you look at what the junior tutor said, they have all the different allotropes of carbon. So this is what diamond looks like. Graphite, you have these graphene sheets that are stacked together. And yep, so this is just more examples of carbon. You can have single-walled carbon nanotubes, and if you have a lot of these walls, you can have multi-walled carbon nanotubes, amorphous carbon. Yep, so it has a 3D structure with multiple stacks of carbon plane that is attached to each other via pi bond. So this solution is correct. Okay, so question 11, calculate the formula of dinitrogen monoxide in an acidic gas called laughing gas. So I'm assuming they want the molar mass. So to find the molar mass of laughing gas, we need 2 times the molar mass of nitrogen plus the molar mass of oxygen. So these are just values you would find on the periodic table. For nitrogen, it's 14.01 grams per mole. And for oxygen, it is 15.99 grams per mole. And we get a value of 44.02 grams per mole. So let's see what the junior tutor said. 28.02 plus 16, 44.02. Okay, so this solution is correct. Question 12 asks, how many pints are in a quart? Okay, so we can just say that there are 2 pints in 1 quart. And the junior tutor said there are 2 pints in 1 quart. 1 US pint is equal to 473 mils. 1 quart has 946.35 mils, so if you divide, you get 2. And even if you had the British pint, 568, a British quart, 1136.52, and divide them, you also get 2 as well. So this solution is correct. Question 13. What are the steps in finding the formula of a hydrate? So I'll write down the definition of a hydrate. So a hydrate contains water with a definite with a definite mass in the form of H2O. So I'm going to write down an example question just so that we can answer all the steps step by step. So let's say we had a sample 210.4 grams of hydrate magnesium sulfate and H2O. So you know you have a hydrate when there is one of those giant bullet points, and then you have a number beside H2O at the end. So this is what a hydrate name kind of looks like. So let's say we had to solve now for the N value. So we have the mass of a hydrate, and now this was heated up. And the final anhydrate, so this means the water was removed when you heat it up, is 120.4 grams. So step 1 is to determine how much H2O is left well, how much of it was removed, I guess. So it started with a mass of 210.4 grams. So this is including the water. And then after the water was removed, I'm going to do minus 120.4 grams. You get a mass of water, which is 90 grams. So step 2 is to convert mass to number of moles. So we do that using N is equal to mass over molar mass. So we found the mass of water to be 90 grams, and the molar mass of water is 18.02 grams per mole. So therefore we have a number of moles of 5. So step 3 is to convert leftover anhydrate to moles as well. So the mass of the anhydrate was 120.4 grams. And the molar mass of magnesium sulfate without any water is coincidentally 120.4 grams per mole. So therefore there is 1 mole of the anhydrate. So step 4 is to find the mole ratios of H2O to the anhydrate. So in our case, it is a ratio of 5 to 1. And then the last step is just to write the formula down. Okay, so the formula is magnesium sulfate, the bullet point 5H2O. Okay, so the junior tutor said, determine the mass of water that has left the compound, which allows us to determine the mass of water that was in the hydrate and the mass of the anhydrate. We do this by subtracting the mass of the anhydrate from the mass of the hydrate. This equals the mass of water. Step 2, convert the mass of water to moles. Divide by the molar mass. Remember that the units for molar mass are grams per mole. When we divide in mass by molar mass, grams will cancel out and we'll be left with moles. Step 3, convert the mass of the anhydrate that is left over to moles. Again, so it's mass divided by molar mass. 4, find the water to anhydrate mole ratio. Generally, you will have more water than anhydrate, so divide the moles of water by the moles of anhydrate. This gives you your mole ratio. If you get a value that is close to a whole integer, then you generally just have to round to the nearest whole number. If your mole number has a decimal that is close to 0.33 or 0.5 or 0.66, you need to find the lowest common multiple of that number that is a whole number and apply it to the entire formula. Step 5, use the mole ratio to write the formula. Yep, so the solution is correct. And I think we have time for one more question. Question 14. How do you convert ATM to Tor? Well, basically, let's say that 1 ATM is equal to 760 Tor. So for example, let's say, what is 3.6 ATM in Tor? We would write x, so our unknown Tor, divided by 3.6 ATM is equal to, on the right side, our conversion factor, 760 Tor divided by 1 ATM. And then we just solve for x. So multiply both sides by the 3.6 ATM. And you'll notice that the units should cancel out. So 760 times 3.6 is equal to 2,736 Tor. That's just an example question. Junior tutor said the same thing. 1 ATM is equal to 760 Tor. 2.1 ATM is equal to 1,596 Tor. So the solution is correct. I think that is all the time that we have for today's session. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description below. And also, if you enjoyed today's video, go ahead and give it a like and a comment. And don't forget to share with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.